Hello everyone, welcome to our discussion of section 9.2 where we will be talking about the dot product. Now of course the dot product is a discussion that will build on our discussion for section 9.1 where we introduced vectors. The dot product is the operation between two vectors that produces a scalar or a real number. So the result of a dot product is not another vector, it's just any number. Now you might be wondering, what is the purpose of this operation? Well, this whole course has been about angles and evaluating angles and such. So this operation, dot product, helps us figure out the angle between two vectors. That is the primary reason why we study it. We won't go into much any more details than that, but you will see this topic again in Calculus 3 if that course is part of your program of study. So for now, we will learn how to calculate the dot product and use that dot product to find the angle between two vectors. Now the definition of the dot product is what you're seeing on the screen now, and it says that if we have two vectors, u and v, with these components, then their dot product is denoted by this notation. That dot is not like multiplication dot, but it's just a dot product, is defined by this operation. So we multiply equivalent components in both vectors and then add the result to get a real number. Like I said earlier, this result itself is not a vector. It's going to be just a number, a scalar. Now in this course and in this section, we will be talking about vectors that have two components. But in Calculus 3, when you go into more details about dot products, you can have apply the same operation to vectors that have more than two components. But this operation stays the same. So if we had a third component here, let's call it C1 and C2, then this would be plus C1 times C2, and so on and so forth. Okay. Now the properties of the dot product, there are several of them. These are basically equivalent forms of dot products. So as you can see, if you change the order of the dot product, it doesn't make any difference. You can either take the dot product of u and v or dot product of v and u. The result is equal. If you multiply one of the vectors by a scalar, and you're taking the dot product of the two vectors, then it's the same thing as if you calculated the dot product of the two vectors and just multiplied the result by the scalar. So suppose the dot product result is, say, 5, and this a is 2, so you can simply calculate the dot product, 5, and then multiply it by this 2, and you get 10. So the result is going to be a scalar or a real number. Here we're adding two vectors and taking the dot product of that result, which is a vector, with this vector. So the easiest way to handle this operation is you add these two vectors and you take the dot product. But what this property is saying is that you can use the distributive property and take the dot product of the vector on the outside of the parentheses with each of the ones on the inside and then add the result. So you get a number here and another number here, and you can just add them up. Okay? These are equivalent forms of dot products. This one is saying that if you calculate the magnitude, remember in section 9.1, where we calculated that without the power, that's the notation for the magnitude of a vector or the size of a vector. recall that a vector has a magnitude and a direction, and that is referring to the magnitude or size or length of the vector. And if you square that, it's as if you're taking the dot product of the vector by itself. It's the same result. Okay? So once again, if you square the magnitude of any vector, it's the same thing as if taking the dot product of that vector by itself. It's the same thing. Okay? All right, so now, next then, we talk about the crux of, or the main reason why we discuss dot products. It's because we're interested in knowing the angle between two vectors. So once we have the dot product, then there's a formula which we can use to find the angle between two vectors. So suppose we have, let's see, well, did I mention a note before that? So I said it in my discussion a minute ago, but let me also add it for the sake of your notes here at the bottom, that note, the dot product is not a vector. It's a real number or a scalar, real number or scalar. So I thought, because this is very important. Okay, I added that. So suppose then, let me draw a little basic graph here. Suppose we have this diagram. And suppose we have two vectors. Let's call one of them vector u, this one, vector u, and suppose the other one is vector, let's say v. And vector v. Okay. So we're interested quite often, what is that angle between them? What is the measure of that angle? And we can use dot products to calculate that. So given two vectors u and v, the angle between them, let's call it theta, as follows. So here's the formula for that. Cosine of theta, cosine of that angle, is equal to the dot product of the two vectors u and v divided by the product of their magnitude. Okay. Very important formula. Like that. Since we're talking about angle, Now, if that angle between the two vectors is 90 degrees, that has a significance. And so let's say a few words about that. If we have two non-zero vectors u and v, these two vectors are called perpendicular or another name for perpendicular is orthogonal. If the angle between them is pi over 2 or 90 degrees. So especially in data analysis, orthogonality of whether the vectors are orthogonal or perpendicular to each other or not has a special significance in data analysis. So if that's the trajectory of your academic progress, if you're considering to become a data analyst in the long run and in graduate school, those are the things that will become very significant at that level. But at this point, we just calculate the dot product and we use it to calculate the angle between two vectors. That's all. And then very closely connected to that, so let me actually, and then I'll write it here. So two non-zero vectors u and v are orthogonal or are perpendicular or orthogonal if their dot product is equal to 0. Is 0, and we want to show that using this formula. So the dot product of u and v is equal to 0. Okay, so that means that these two vectors are perpendicular to each other. Okay, so let me, actually this is so important that I want to put the whole thing in a box. Like that. Okay. So we'll do some examples to see how all of this works. So in this example, we say that given two vectors in component form, so let's say vector u that is equal to this, and vector v that is equal to 1 comma negative 1, given these two, we want to find the dot product of u and v. And remember that whether we're looking for the dot product v dot u or u dot v makes no difference. They're the same value. Okay? So as the formula said, let me bring back the formula. To calculate the dot product, we multiply their equivalent components and then add the results together. Okay, so let's do that here. So we have, so this is equal to minus, or let me start it in component form. So negative 6 comma 6 dot product of 1 comma negative 1. That would be equal to now negative 6 times 1. That's negative 6 times 1 plus 6 times negative 1. Remember the ij forms? So this is multiplying the I terms and add the j terms to them. So 6 times negative 1, and of course we get negative 6 minus 6. 6 times negative 1 is minus 6. So we get negative 12. So notice, as we said, the dot product of two vectors is a scalar, not a vector. It's a number, just like that. Okay, so that's part A. Part B, we want to, of course, do what we said was important for us to be able to do, which is find the angle between those two vectors. So find the angle between u and v. And we want to do that to the nearest degree. Okay, like that. Okay, so the formula for that we just introduced is that first we're going to find the dot product of the vectors, then divide it by the product of their magnitude, which we learned how to calculate in section 9.1. And that's going to give, this ratio is going to give us the cosine theta. So how do we calculate theta? Because that's what we're interested in. Well, we learned that theta is equal to the inverse trigonometric function. So it would be inverse cosine of this quantity, which would be equal to theta. Okay, so let's do that for this example. So we know that the cosine of theta is equal to u dot v, the dot product, divided by the magnitude, the product of the magnitudes of both vectors. So we already have that, right? That's negative 12. So let's plug it in. And we're going to, let's see. Okay, that's better. So we're going to say cosine of theta is equal to minus 12 divided by, so the magnitude of vector u would be square root of negative 6 squared plus 6 squared, right? And then times the magnitude of vector v, and that would be a square root of 1 squared plus minus 1 squared. Okay, so let's simplify this expression. we have cosine of theta equals negative 12. That would be 36 plus 36 square root of 72. And times, this would be 1 squared is 1, negative 1 squared is 1, so this would be square root of 2, right? Square root of 2. And then, of course, so let's see. So my numbers agree with that so far. And cosine of theta, it's minus 12 divided by, at this point, I'm going to I calculated these. So I got, this is what I got, and 8.48528. Please don't take my word for it. Calculate these numbers and see if your numbers match this. Times square root of 2, which of course is an irrational number, so we have to then just take. I usually, in between my calculations, I usually keep up to 5 decimal places. Okay, I don't want to round these numbers too early because my final answer will turn out to be very different than the actual answer. So I think keeping it to 5 decimal places keeps the calculations fairly accurate. Okay, so then multiplying those two in the denominator, we get cosine of theta equals minus 12 divided by virtually 12. So this is what we get, virtually 12, right? So what this tells us that cosine of theta, it's really equal to negative 1. Now this is an easy angle. You can write, if you want, you can write theta is equal to inverse cosine of negative 1, and then say that, okay, what angle has a cosine of negative 1? It's pi, or 180 degrees. But this is an easy number to calculate, and I mean, you don't have to even calculate this. You'll probably remember it from the special trigonometric values table. But if this number is a little bit difficult or not something that is on the special table of trigonometric values, then you'll have to use the calculator with the inverse cosine function for it. Okay, and we'll do that. So this would be, so theta is equal to 180 degrees, and that's the angle between those two vectors. Okay. All right, so let's do another example. And I want to grab my calculator because sooner or later that is going to come up, and I'll need to show you guys how that works. Okay, like that. All right, suppose in this example we are given two vectors again. And this time we're given these vectors in ij form. So we know that this is minus 5j, so there's no I component for this. Or there's no horizontal component, we just have the vertical component. Remember that from section 9.1? And V is equal to minus I minus square root of 3j. So this one we have both a horizontal and a vertical component. So given that, we're asked to first find, of course, the dot product. Okay. All right. So let's convert these to their component form. Right now they're in ij form. So we know that u, or so here's the solution for that. So u equaling minus 5j, that is the same thing as saying u has components equal to 0. The I component, or the horizontal component, is missing, so it's 0, comma, negative 5. Okay? By the same token, for vector v, which is negative I minus square root of 3j, the component form is, the vector component form would be equals negative 1, comma, negative square root of 3. Okay? All right, so now we can calculate the dot product. Which is equal to 0, comma, negative 5 times negative 1, comma, negative 3. Okay, and then simply we carry out according to the formula that we showed, which is 0 times negative 1 plus negative 5 times negative square root of 3. So take the product of the equivalent components and then add them together. Okay, so this would be 0, and then minus 5 times minus square root of 3 is simply 5 times square root of 3. So that's the dot product. And then, of course, the next thing we have to do is find, for part B, we have to find the angle between those two vectors. So let's do that. So find the angle between u and v. Oops. And we want to do this again the same way we did it in the previous example. We want to do it to the nearest degree. Okay, like that. Okay, so the formula for this operation is cosine of theta equals the dot product of the two vectors divided by the product of their magnitude, right? Like that. That's our formula. So we already have that, which is that. We calculated that in part A. Now, because the vectors are now off the screen, let me, because we want to work with those, I'm going to write them here again. So we have them in front of us as we go through this operation. So we have, these were the vectors. We had u equals minus 5j, actually j, and v is minus I minus square root of square root of 3j. Okay, so let's find the magnitude of these two and multiply them together. So we have cosine of theta equaling 5 square root of 3, right? Divided by the magnitude of u. What would that be? Because I is already 0, so minus 5 squared. That's all we have. Negative 5 squared times square root of negative 1. The coefficient of the horizontal component is negative 1, that coefficient. So negative 1 squared plus negative square root of 3 squared. Right? All right, so cosine of theta is equal to 5 square root of 3 divided by, this is simply 5, right? Square root of 5 squared, negative 5 squared is just 5, so that's that. Times, we have square root of, that's 1 plus 3, right? That's negative square root of 3 squared is just 3. So we have cosine of theta equals 5 square root of 3 divided by 5. Square root of 4 is 2. 2 times 5 is 10. And then, of course, we can simplify this and write cosine of theta is equal to square root of 3 over 2. Now, you can write, if you want, you can calculate it. You can say theta is equal to inverse cosine of square root of 3 over 2, right? You could do that. But in this case, we know that this is on the special table of trigonometric values, and the cosine of pi or 30 degrees or pi over 6 is square root of 3 over 2. So we already know theta should be 30 degrees. But if you want, let's do that on the calculator, because this is important that you should know both ways. You should remember it from the special values table, or you should be able to use your calculator to calculate that. I want to make sure that my calculator is set to degrees first before I carry this operation. You can see that it is set to degree, right? It is set to degree, so I'm okay. So I'm going to exit that. Then I'm going to activate the inverse cosine, which is that. And then I'm going to put in square root of 3 over 2. And we should get, and the setting was in degrees, so we should get 30 degrees. Let's see. Oops, what did I do wrong? I must have done some, okay, let me try this again. So inverse cosine of square root of 3. I don't know, it might give me trouble about this. 3 divided by 2, like that, and like that. For some reason, it's giving me, as you can see, it's giving me, let me try this way, cosine of square root of, if this doesn't work, I'll try another way to get it to work. So no worries there. So square root of 3, let's see if this trick will work. I'm going to eliminate one parenthesis. No, it's okay. So let's do it this way. Let's first calculate square root of 3 over 2. Like that, right? And I'm going to take the inverse cosine of that. So let's do that and see if this calculator is going to give us the right number, which is 30 degrees. Okay, so something is not set up right. Let me use my other calculator. This one, I have to look into that to see what's going on. But I'm going to grab my other calculator. So here's a smaller one. So again, I'm going to check to make sure that the screen is more difficult on this calculator, is more difficult to see on the screen. So that's why I was using the other calculator. But I hope you can see the screen. So I'm going to make sure that the calculator setting is in degrees. In fact, it is. You can see it's set to degrees. So then let's exit out of this. So clear that. All right. So we want to activate the inverse cosine and then take the input, the cosine of square root of 3 divided by 2. For some reason, this isn't, that's interesting. So let's see. Well, does it give us the, if I change the, this is important part of this course too. You should be able to use your calculators for this. So I'm going to switch the mode here to radians. I have no idea why this calculator is refusing to calculate that. That's a perfectly valid calculation. So cosine of square root of 3 divided by 2. No, it's still okay. I'm not sure what's going on, but we should have maybe, well, oh, that's the problem. That's the problem. I see what the problem is now. Okay, so the square root is calculated over 3/2, which of course would not be correct because cosine varies between -1 and 1, but because of the way the parentheses were showing or capturing that number, it was as if I'm taking the inverse cosine of square root of 1.5. So, and that's not gonna, so that's the problem. So here's the fix for it. I'm going to take the inverse cosine of square root of, this should work. This should work. So let's see. Square root of 3, and I'm going to close the parentheses. I should have done that. Okay, so now I close the parentheses, and I'm going to divide that by 2. Now close the parentheses, and now we should be able to see, yes. So, and that's in radians, because I just changed this. So let me go back and change it to degrees mode, and everything should be back to normal. Okay, so that's degrees. And we're going to repeat that, and this time we should get 30 degrees. Okay, so let's see. So that sine of 3. So that's what I should have done. Close the parentheses because it's square root of 3 over 2. Notice we have square root of 3 over 2. What I was putting into the calculator was square root of 3 over 2, the whole thing under the square root, which is not correct. Now that's correct. So divided by 2 and close the parentheses, we should get 30 degrees, which is the right answer. Okay. Okay, so that's the result, and therefore we have 30 degrees. So right now, actually, if you ever wondered why you should memorize the table of special trigonometric values, with this calculator issue that I had, you can make the argument that, okay, it was worth it, because if you remember that table, you wouldn't have to use the calculator and have such issues that might waste your time during an exam. You could just write down 30 degrees. Okay, but I'm glad I got into that trouble, so you could see that just minor things like where the parentheses are located in your calculations on a calculator can make a huge difference. All right, so let's move to another example. So in this example, we want to determine if the following vectors are perpendicular or not. Remember, if the dot product of two vectors is equal to 0, then that means that the two vectors are perpendicular to each other. All right, so determine if the following vectors are perpendicular. And you should be familiar with both terminologies, so I'm going to add i.e. the vectors are orthogonal. Okay. So we're going to do several examples of this type. To be exact, we're going to do maybe 3 or 4. Well, we'll do several. Okay. So part A, given the vector u that is equal to 6, 4 with these components, and vector v that is equal to -2, 3, then here's the solution for that question. So we take the dot product, and this would be a good time for you to pause the video and then come back once you have your own solution. So we have 6 times -2 plus 4 times 3, and we have -12 plus 12, which is 0. So definitely these two vectors are perpendicular to each other. So yes, u and v are perpendicular. Okay, let's do another example. For part B, suppose our vectors are u equals 2i And so we have a horizontal component for this vector, but not a vertical component because j is missing. And v, vector v, is equal to minus 7j. Okay. Well, by now you know how to write the vector component form from this ij form, so I'm just going to do that right away. So solution would start here. So from here we know that u is equal to 2 comma 0, right? And from here we know that v, or vector v, is equal to 0 comma negative 7. Okay, so let's take the dot product. And we have 2 times 0 plus 0 times negative 7. Of course, these are just 0. 0 plus 0 is 0. So again, the dot product is 0, which means the two vectors are perpendicular. So once again, yes, u and v, vectors u and v are perpendicular. Okay. So let's do one more example of this kind. Suppose we have a vector u that is equal to 4i. So once again, the vertical component is missing. And vector v is equal to minus I plus 3j. Okay. So from here, let's write the vector component form. We have u that is equal to 4 comma 0 and v, vector v, that is equal to negative 1 comma positive 3, right? So let's find the dot product. So we have 4 times, let's see. Okay, so 4 times negative 1 plus 0 times 3. What do we get? We get negative 4, right? This is not equal to 0, so the vectors are not perpendicular. Okay, so vectors are not perpendicular or orthogonal. They are not orthogonal. Okay. So I want to actually box these. So they were perpendicular there. They were perpendicular here. But here the vectors are not perpendicular. Okay. All right. So let's do more examples. So suppose now we have three vectors and we want to take their dot products, or we want to carry out some kind of operations involving dot products on three different vectors. Okay, so let's do a few examples like that as well. Okay, so given these three vectors, and then V and also W we want to find this result. Find U dot V, vector V plus vector W. Okay, we want to find that. Okay, so now this, what I would do, you could use the distributive property like we discussed earlier. You could take the dot product of U and V and then say plus dot product of U and W. You could do that. But I prefer to just add those two vectors and then take the dot product of the resulting vector with U. Okay, let's do that. So we have V plus W so V plus W, right? Let's add the equivalent components, the horizontal components. 1 plus 3, that would be 4, right? Or 4i, if you prefer. It makes no difference. So 4, and then minus 3 plus 4, that's positive 1. And then, of course, U is 2, comma 1. Let me write it here. U, since I switched from ij form to this vector component form, I'm going to do the same thing for U, and I'm going to say 2, comma 1. Okay? Now we're taking the this dot product. So therefore, from here, we can say that U dot product of that is equal to this is that, right? So we take 2, comma 1, take the dot product of it with 4, comma 1. Oops, sorry. Let me move this up a little bit. So what do we got? We got 2 times 4 plus 1 times 1, and we get 9, right? So there's that result. Let's do another example of the same kind. So part B, suppose we want to find, given the same three vectors, by the way. I'm going to write them down so we can look at them on the screen. So find this result. We have find u plus v dot product u minus v, vector v. Okay, so each of these is a vector, right? We can find this vector, add these two vectors, get that vector, subtract these vectors, get our vector, and then take the dot product of those results. Okay, let's do that. So, and as I promised, let me write those vectors here again. And we have u equals 2I plus j. V is I minus 3j. And we have w equals 3I plus 4j. Okay. All right. So first let's find u plus v given these vectors. So we have u plus v, vectors plus v equals, so what are we going to get? We're going to add the equivalent components. So 2 plus 1, 3i, right? So 3i. And then 1j minus 3j, that would be minus 2j. So minus 2j. And then let's find this one, u minus v. So u minus v. So that would be 2 minus 1. That would be 1i, or I. Then 1 minus minus 3. That minus 3 would make this minus 3 positive 3 plus 1, 4 plus 4j. Okay. I forgot to remind you, but I hope you've paused the video before you see my solution and have worked these out on your own before you see the rest of the solution. But now we have figured out each of these vectors. We can easily then take the dot product, right? So let's do that. So therefore, we have u plus v and dot product u minus v is equal to, let's use their component, vector component form. We have 3 times 1, right? So 3, let's see. Well, let me just write them like that. So 3 comma negative 2 dot product 1 comma 4. Okay. Then we have 3 times 1 plus minus 2 times 4, and we have minus 8 plus 3, or minus 5. Okay, like that. All right, so let's do one more example so we feel really comfortable with these things. So this whole course is very, very procedural, as I mentioned before. So the more practice you get with these, the better you will be at all of this. So let's call this part C. And we want to, given the same vectors, so let me, I will write those again on the screen so we can look at them. So we want to calculate this result. U dot V, the dot product of those two vectors, multiplied by U, the dot product of U, vectors U and W. Okay, and the vectors were as follows. And given, so we have, let me write them on this side, U equals equals 2I plus J, and V, vector V, equals I minus 3J, and W equals 3I plus 4J. Okay, you want to pause the video if you haven't already. Please do that. Carry out this operation and come back to see if our answers agree. So I'm counting on you that you've done that, and now you're back. So what I would do is first calculate this dot product, then calculate that dot product, and then multiply the results together to get the final result. Okay, so I will begin by saying, so from here, from that one, we have, and looking at these, of course, right? Looking at these. So we have the dot product of U and V, right? So what do we have? U is 2, 1. Dot product V is 1, negative 3. And so let's calculate this before we go to that one. So we have 2 times 1 plus 1 times negative 3. And what do we have here? We have 2 minus 3 plus 2, that's minus 1. Right? Okay, so let's calculate the dot product U and W. So we have U is 2, 1. W is 3, 4. So 2 times 3 plus 1 times 4. We get 6 plus 4, that's 10, right? So now we can simply multiply negative 1 times 10. So let's do that. All right, minus 1 times 10, and the final result is negative 10. Like that. Okay, so this is pretty much wraps up our discussion of section 9.2, which is the topic of dot product. So please remember, the main reason we study it in this course is to find the angle between two vectors. I thank you for watching this video until the end. I count on you to let me know if you have any questions, and I look forward to see you again next time. Until then, have a nice day.